In this video, I'm going to talk about mechanical and electromagnetic waves. So in the last video, I introduced the idea that there's two main types of waves, longitudinal and transverse. They're basically different ways in which the particles in a wave can move. And now there's also sort of two general categories of waves that we see in nature. So there's mechanical waves and there's electromagnetic waves. Electromagnetic, EM for short, because physicists were very sloppy and lazy. Shorthand for electromagnetic. Okay, so what's a mechanical wave? Mechanical wave is basically any type of wave which requires a medium, aka a substance or matter, to travel through. So it's a wave which requires a medium. Okay, physicist's way of saying matter or a substance, that could be a solid, liquid, or gas, to travel through. And longitudinal and transverse waves, they're both examples of mechanical waves. Okay, they both need something to travel through. So e.g. a longitudinal and transverse. Okay, transverse, so water waves, for example. Water waves, they need obviously the water itself, right, to travel through. Longitudinal, you've got sound, so sound needs air to move through. You've got seismic waves, aka earthquakes. So seismic waves, they need the earth to travel through, the different layers of the earth. Slinkies and springs. Springs as well. So that's what mechanical waves are. They're basically things that need something to travel through. And they can be longitudinal or they can be transverse waves. Electromagnetic waves, on the other hand, something a bit different. So here's the origin of electromagnetic waves. So if you have a charged particle, let's take an electron, negatively charged, and it's moving, that will create a magnetic field, okay, along its direction of motion. So it'll create a magnetic field. Okay, if you think of let's take a wire, let's say. Let's take a circuit. Okay, let's take a battery. Let's take a battery here. Wrap some wire around the battery. And let's put a compass needle nearby. What will actually happen is the compass needle will deflect, okay, provided the current is strong enough moving through the circuit. And the reason being is because electricity can create magnetism, and magnetism can then create electricity, and vice versa, and so on and so forth, I should say. So moving charges create a magnetic field. Okay, that's one of the fundamental principles of electromagnetism, the study of electricity and magnetism, their union. So a current can make a magnetic field, okay, and the compass needle itself has a magnetic field. And so the magnetic field from the current, okay, interacts with the magnetic field from the compass, and that's why the compass needle deflects. Okay, so current creates a magnetic field. A magnetic field can then create a current ad infinitum. And a very brilliant Scottish mathematical physicist named James Clerk Maxwell in the 1860s theoretically proved that light is an electromagnetic wave. Okay, James Clerk Maxwell, light is an EM wave. Okay, the mathematics isn't really that complicated. You really need just basic calculus. It really depends on what type of the version of his equations that you deal with, if it's the integral form or differential form, as they're known as. But he basically used maths to prove that light, C, okay, the speed of light is 300 million meters per second. Out came this number miraculously from using things like electric and magnetic fields. So electric fields, these are things which come from charged particles. So a plus charge, its electric field looks like this, okay? Field lines are things which surround an object, in this case a charged object. For a negative charge, the field lines act towards it, okay? And that's why positive and negative attract. Positive and negative charges attract because the field lines go from the positive to the negative, right? The negative takes it in. So light is an electromagnetic wave. It basically looks like this. It's a transverse wave. So electromagnetic waves, they're transverse waves. They can only be transverse waves. Light looks like this. You've got up and down motion. You've also got back and forth motion like this. Light is made up of electric. Okay, E for electric. Arrow on top means vector. Okay, vector. A vector in physics is something which has got a size and direction. So the electric field here is acting along the y-axis. It's going up and down. It's going up and down, vibrating up and down, if you like. And the magnetic field is at 90 degrees to that electric field. Okay, it's going back and forth. Capital B for magnetic field, just by convention. It's not M for magnetic field. M is used for something else in physics. Things like, for something like magnetization. And that wave here, so light is self-propagating. It's a self-propagating wave. What does that mean? Well, it means that an electric field creates a magnetic field, that creates an electric field, etc., etc. And this happens at the speed of light, at this particular speed. So that's what light is. And light, to me as a physicist, light means this. Light is all of this. Gamma rays, X-rays, gamma rays, ultraviolet radiation, microwaves, radio waves, visible light, infrared light, aka heat. All of these are the same thing. Okay, this is light. X-rays, the only difference between X-rays and, let's say, visible light, so the light that we use to see, the only difference is the energy. So X-rays look like this. They've got a really high frequency, which is why they're so good at what they do, at penetrating human flesh to see bone. X-rays look like that. Visible light, let's say, looks like this. Okay, that's why obviously the light coming from your smartphones or from your TV isn't deadly. It's low energy. But yeah, light is a electromagnetic wave. It's a transverse wave. And the thing with light is it doesn't require a medium. It doesn't require anything to travel through. It can travel through empty space. It can travel through vacuum. Doesn't need a medium. Okay, unlike mechanical waves, which require a medium. So light from the sun, it takes about, so here's the sun, takes about, here's the Earth, about 8 minutes to reach the Earth. That gives you a good insight into how far away the sun is actually. So that's why we can see light from the sun, because it can travel through empty space, not a problem. Now, what are the commonalities? What are the similar things? What are the things that mechanical waves and electromagnetic waves share? Well, both mechanical and EM waves, so they both carry energy. Okay, all waves carry energy. And they don't transmit matter. Okay, they don't carry anything that's physical. And that's electromagnetic waves and mechanical waves in a nutshell.